Hello everyone. Thank you for joining today's webinar on rapid prototyping for big data with AWS. And now let me introduce to you our today's speakers. This is Serge Aziv, VP of Technology Services at SoftServe, Taras Baczynski, Data Architect at SoftServe, Vadim Astahov, Solution Architect at AWS, and Ariel Weil, VP of Marketing and Business Development at YOTTAA'S. So hello guys, and I think you can tell a couple of more words about yourself when you will introduce what you're going to talk about. So let's start.
Thank you, Olha. Hello to all our attendees. This is Serge Aziv speaking. It's my pleasure to share with you some of SoftServe best practices in big data and specifically in rapid prototyping. Let me briefly overview the agenda for today's webinar. We will start with outlining big data prototyping, addressing main questions, what are typical big data challenges and when and why to prototype. Then my colleague from Amazon Web Services, Vadim, will highlight AWS services that enable creating sophisticated big data solutions in clouds. The AWS on-demand pricing model allows greatly reduce the cost of your big data prototype. The second half of the webinar is dedicated to a case study based on YOTTAA'S traffic analytics platform. Ariel and Taras will present the business needs and how prototyping based on SoftServe best practices and AWS environment helped achieve the project goals. And at the end of the webinar, we'll have a chance to answer your questions. If you have any during our webinar, please don't hesitate to send them to webinar@softserveinc.com. So what are typical big data challenges? To answer this question, let me first recap that big data is data that is too large, complex, or dynamic for any conventional data tools to ingest, collect, process, and analyze. Since nowadays there is no longer one-size-fits-all traditional solution for all business needs, a big data solution design and selection of modern tools is quite challenging. There are so many factors that drive your technical decisions. These are different data sources and requirements to data volume, variety, and velocity. These are architecture concerns such as scalability, performance, extensibility, cost, and even skills availability in modern tool set on the market. In addition to that, the technology landscape is evolving drastically. New technologies are appearing every month, and their marketing capabilities typically are far ahead from real technical ones. As a result, pure architectural and technical analysis may not be sufficient to address all these complexities. Why prototyping is important? Sometimes you may hear managerial stereotypes that prototyping is expensive, but in fact, when used properly, this is one of the most effective tools to deliver a big data project successfully in time and budget. Typical signs when you need to consider prototyping, even if you have experienced team of engineers. These requirements are uncertain, technologies are new, no comparable system has been previously developed, and no full buy-in from the business. The last one is more about business decision rather mitigating technology risks, but still can leverage best practices in big data prototyping. In general, we distinguish 4 types of prototypes. Each serves for a certain purpose. Horizontal prototype is a common term for a user interface prototype. In reality, it can be a set of wireframes or mockups to explore and demonstrate the range of abilities of a system, created by user experience or data visualization experts. Vertical evolutionary prototype can be an effective risk mitigation strategy if it's implemented as a skeleton into which components and technologies can be integrated. This helps to mitigate integration risks supports early demonstrations of end user value, and aids in the understanding of end-to-end scenarios. Throwaway prototypes, also known as rapid prototypes or proof of concepts, POC, work best when we need to quickly evaluate a technology to see if it can satisfy critical architecture scenarios, usually related to quality attributes such as performance and scalability. A throwaway prototype often is used for narrow scenarios that focus on the evaluation of just one or two components. And last but not least is minimum viable product, or MVP. The decision to create MVP is a business decision more than one simply driven by technological risk. Typical business goals include getting early feedback from end users and updating the product accordingly, presenting a working version to a trade show or customer event, structuring the development process, and checking team progress and alignment. Now, when you learned about different types of prototypes, you may think, when is the right time to introduce it in the project development cycle, and what goals each prototype should aim. Here is the generic prototype lifecycle we recommend. Start with initial architecture analysis to create architecture design and select candidate technologies. Do rapid horizontal prototype using UI wireframes or mockups if the system features are wide and you need to confirm scope, or you need to obtain buy-in from the business to demonstrate the future system. Continue with vertical evolutionary prototype. Its code will be a foundation of your final product, and you can test critical functionality at early project stages. Rapid throwaway prototype or POC can be parts of vertical evolutionary prototype or development iteration spikes to validate technologies and scenarios that pose risks. And the above steps lead to MVP, which is a first working version, if you will, of your production system. Please find more details about big data prototyping best practices in a fresh IEEE Software Magazine issue. In the article Strategic Prototyping for Developing Big Data Systems, written by SoftServe, SCI, and University of Hawaii Associates. And now let me pass the webinar topic to Vadim Astahov, Amazon Web Services.
Thank you. It's Vadim Astahov. I'm Amazon Solution Architect. Within Amazon, I'm supporting our national consultant partner, and it's my pleasure to support you guys today. So, all right, so let's start and talk about some big data challenges. In the modern world, data is produced with ever-increasing volume, velocity, and variety of the forms, and those data can be extremely valuable. It can be understand and track application or service behavior, so we can find the errors of suboptimal user experience. We also can mine the data for the patterns and correlations to generate recommendations and forecasting. Examples can be e-commerce sites, which analyze user access logs and provide product recommendation. Another example can be social networking sites or dating sites, which provide new friends recommendation or helps to find qualified soulmates and so forth. Also, we found that customers and businesses in our days are demanding up to a second or even millisecond analysis on their fast-moving data, in addition to classic batch processing of historical data. We're also finding that data creation has become more real-time and continues to, there is a new need to manage it at high speeds. And here at AWS, we present it as a data bus when we talk about big data. This data bus is comprised from various stages, such as ingest, store or collect stage, process, and finally analyze and present data for visualization. The right technology in each stage based on criteria like data volume, data structure, as well as required query latency, request rate, and item size. AWS delivers a variety of technologies to accommodate all those process stages. Here you can see extensive portfolio offered to deal with various aspects of big data. But the question remains, what services should we use, when, why, and how? And the first typical question we have is, how can I move my data to AWS? Here you can see that on the top side, three options that provided. First is AWS Direct Connect that basically allow you to establish dedicated network connectivity between your network and one of the AWS Direct Connect locations. This service provides you with dedicated bandwidth and consistent networking experience. Another service is AWS Import-Export or Snowball, which is petabyte-scale data and transport solution, which is literally provide you with a hardware appliance that allow you to migrate terabytes of data. Also, we're working with a variety of the partners that provide the solution for internet acceleration techniques that allow push you up to a few terabytes of data daily through the public internet. When data start moving into AWS, we can persist them in a number of storages for further analysis. Those services are Relational Database Service, RDS, Object Storage, S3, Streaming Storage Solution like Kinesis, and Key Value Storage, DynamoDB. Also, Hadoop File System, HDFS, on Elastic MapReduce, and Redshift Warehouse give you a wide range of options to persist the data. What data storage should we use and when? Here at Amazon, we don't believe that there is one single tool that can do everything, but rather you can use the right tool. You can build highly configurable big data architecture to meet your specific needs. And AWS comes with a variety of services which provide customer with the right tool optimized for the data structure and query complexity. Here you can see our services grouped in 4 major classes based on the data structure and the query complexity. As you can see, top 2 quadrants represent structured data, and the bottom 2 represent non-structured data. At the same time, started from the left to right, left column group services which provide well optimized for simple query patterns, while 2 groups on the right-hand side present services optimized for complex query. Let's go into little details. On the left top side, for structured data and simple query capacity, we offer DynamoDB key value storage. Also, you can leverage a cache solution like Elastic Cache that support 2 major engines, Memcached and Redis. On the left bottom, for unstructured data with simple query patterns, obviously the S3 storage and the Glacier as 2 solutions. On the right-hand side, top, for structured data with complex query capability, we offer Amazon RDS with a variety of engines like Postgres, MySQL, Oracle, SQL Server, and the new service Aurora, and also data warehouse solution Amazon Redshift. And for non-structured data or semi-structured data which require high complex querying, semantics, we offer Cloud Search and Amazon flavor of Hadoop, Amazon Elastic MapReduce service. Another way to think about data, big data, design for optimal solution is a frequency access pattern, which can be visualized as a data temperature. Data labeled as a hot if they are very frequently accessed by the customer, probably within a few seconds or millisecond time window. On the opposite time scale, we can see the cold data, which are typically archived data with rare chance to be accessed, or can tolerate hourly delay access. Warm are typically referred to the data which access pattern from a few seconds to a few minutes. Other parameters such as total volume of data, item size, request rate, and query latency, as well as durability and cost, play equally important role to build a highly configurable big data architecture and meet the customer requirements. Usually for hot data, we're talking about the small data object within a few kilobytes, a total volume, a few gigabytes at most. But usually we expect small query latency and high request rate. While we're talking about cold data, then it's usually big data volumes with low request rate for data and response time for processing within a minute, if not an hour. Now, here you can see the heat map, which combines the notion of data temperature with query latency, and it summarizes AWS solution available in the context of temperature of data and the data volume. Also, it takes into consideration data durability, request rate, processing latency, and the pricing requirement. As you can see on the left-hand side, Elastic Cache and DynamoDB are good fit for hot data, while RDS, Cloud Search, EMR with Hadoop file system, and S3 provide you good options for warm. And finally, on the right-hand side, Glacier is offering for the cold data. But there is certain intersection in terms of latency, request rate, and data volume among Elastic Cache, DynamoDB, and RDS. And also another group is DynamoDB, RDS, and Hadoop file system. Thus, as you can see, our customers always have a few options to implement their solutions. And finally, to provide a complete toolset for the big data problem, AWS provides processing application called connectors, which can write to multiple data stores and processing frameworks such as Storm, Hive, Spark, and so on, which actually can rely on the multiple data sources. This diagram illustrates a variety of connectors that allow you to channel various services. For visualization, AWS also working with many partners to provide the business intelligence platform, which can be connected to AWS Big Data Service through standard API calls. Thank you. And with all of that, I will pass to my colleagues.
Hi, everybody. This is Ari Weil from YOTTAA. Just really briefly by way of introduction, I run marketing and business development here at the company. And to explain a little bit briefly about what YOTTAA does, we're a cloud-based platform that looks to optimize web and mobile applications in real time. And the way that we do that is by focusing on the way that modern applications, especially web applications, have been architected, which is increasingly using as-a-service components. So, in the CDN space that we compete, there are a lot of legacy implementations of code that people are looking to modernize. There are lots of companies who are coming and starting to compete as new entities in the market. And most people are coming to market very quickly using things like Amazon, AWS, or Microsoft Azure for the infrastructure. From a platform perspective, looking at turnkey solutions like, for example, Demandware for e-commerce or Acquia for content management and media. And then the just huge array of applications that you can implement via JavaScript that are SaaS components that extend your applications. And what YOTTAA does is to create an abstraction layer across all three of those areas and then works as a proxy. So the interesting thing is we can see as a proxy every infrastructure response to every end user request. And so basically our network architecture ends up looking like this, where we sit in between a series of different network components. Now, the incredible opportunity here is for us to give insight not only to our own network operations team, but to all of our end user customers in order to really understand the dynamics of how their application is behaving, how users are interacting with that application, and how the different infrastructure components are responding to those requests. YOTTAA acts like an application delivery controller in the cloud, making intelligent decisions about routing, about transformation, and about acceleration and security so that we can ultimately optimize an application. What we really needed as we looked at our platform was a way to capitalize on all of this wealth of data, and at a very high rate of speed, the click rates for our end users being something that we wanted to expose to our end users so that they could understand what was happening. because ultimately, when you look at a map of all of the third-party resources that are being requested through an application and the way that business users are thinking about those, the business users are thinking, I want to be able to support my customer throughout their life cycle and gain insight into every aspect of that customer journey. From discovery, where the focus is on search engine optimization, to exploration, where the focus is on speed, and then all the way through ongoing engagement with the platform, where personalization, product recommendations, localization, et cetera, are really key components. If you look at that same business problem from an IT perspective, then you get a request map like the one that I'm showing on the right side of the screen, where you just have such a dizzying array of third-party content, of non-local domains, and real-time changes in the behavior across the landscape, that for them to understand using a simple, for example, Google Analytics JavaScript tag what's happening, it just simply can't provide the insight that people needed. And so what we turned to the experts at SoftServe for help with was how to, as quickly as possible, act as an extension of our own team, given their expertise using cloud-based services like Amazon's that were reviewed earlier in this webinar, and very quickly snap into our development deployment process with a prototype that we could then vet with our customers, and then do ongoing implementations to roll out a real-time dashboard, which is what you see here, that every 5 minutes is giving all of our customers, including massive global organizations, insight into every request and response for things like optimizing end-user quality of service, eliminating the threats posed by DDoS attacks by seeing the impact of malicious traffic in real time and taking action through a web application firewall, and then finally understanding the crushing impact of bots on performance and scalability and taking action to throttle those. And so if I turn it over to my colleagues now to explain how they implemented it, we can move on.
Okay, thank you, Ariel. So my name is Taras Baczynski, and I work at SoftServe. And actually, I was involved in design and implementation of YOTTAA Impact Analytics as a data architect. So we started project from the discovery phase in order to clarify use cases and associated requirements, identify significant architecture drivers, suggest solution, and evaluate our decisions. And among considered solutions, we selected Lambda architecture approach, and the diagram on the slide illustrates the concept of the Lambda architecture. The same data being processed using two layers, batch and speed layer. So why Lambda architecture? Please take a look to architecture driver section, and you'll see two drivers marked in orange. This is near real time and historical view. And in our system, we link events that occur at the same moment in time in order to analyze how one event can impact others. And near real time is highly important quality attribute because it allows to detect events immediately. As a result, improves times to reaction, which is highly important for operational intelligence. The classical examples, and you analyze traffic normally using live data. You identified the source of issue, and then you throttle traffic segment in order to prevent service unavailability. So you need recent data for these operations. At the same time, you need historical metrics such as last month or even last year average and peak traffic. For example, if you're planning to increase your website capacity and be prepared to Black Friday. In this case, historical view intended to facilitate your decisions. You know what happened in the past, so you can estimate your future traffic. Returning back to Vadim's discussion about data temperature, you can see that we also deal with the hot, warm, and cold data. So basically, utilization of different technologies or techniques over cold, warm, and hot data is heart of Lambda architecture. Speed layer serves recent data, which is hot data, and batch layer serves all data or cold and warm data. First, what you see on this slide is selected technology stacks. However, I'm not going to dive into reasoning why we selected these technologies. I would like to concentrate on evaluation process and prototyping in particular. What is important that in our system, all critical use cases and scenarios are related to operational intelligence and near real time. That's why we were mainly concentrated on speed layer, because we saw the following risks. First, Elasticsearch aggregates had been introduced not so long ago, so we didn't know if we can achieve near real time and required query performance. Second, we decided to use open source library for consuming data from Kafka into Elasticsearch. Of course, there were risks associated with this decision. First of all, this is compatibility and throughput of the component. And at the same time, there were no risks associated with the batch layer. However, as you can see, we implemented peak and hive jobs during evaluation phase. You can see on diagrams that batch layer is not hidden as a serving layer and Redshift, right? So the answer is simple. We started from POC in order to evaluate Elasticsearch aggregates. And for Elasticsearch load testing, we needed component which could load web logs into Elastic. So instead of investing time and money in implementation of Kafka Elasticsearch consumer, we deployed EMR cluster in few clicks and created web logs processing pipeline using Hue, Peak, and Hive, which is much faster than implementing custom application. So we successfully evaluated Elasticsearch and started vertical evolutionary prototype in order to evaluate compatibility of selected open source library and integrate speed layer components. Please take a look to diagram on this slide. Risk mitigation on early stages is highly important because the cost of architecture redesign implementation phase is very high. That's why instead of implementing use cases, we concentrate on risk points. So how to ensure that you are in the right track? First of all, you need to identify and document the risks and choose the right evaluation strategy for your solution. As Serge mentioned, there are 4 strategies like horizontal and vertical prototype, POC, and MVP. And especially for the specificity of the big data projects is that influence of technologies, and I talk about both software and hardware aspects. We already covered some of these aspects when we discussed how warm and cold data, about our discussion about warm and cold data and Lambda architecture, right? However, please take into account that each big data project itself could be very specific. Based on our experience, tactics or hardware configuration applied on one project will not work for others, even if this is 2 projects with very similar use cases and scenarios. Why? Well, it's because workload is different, number of concurrent users is different, or even prioritization of architectural drivers could be different. So how to determine what hardware configuration you need? Of course, you need to try, and actually you experiment with hardware configuration again and again, and you will be surprised how number of concurrent users could affect your existing solution, how required CPU, memory, and disk balance could be changed when your workload had changed. Of course, you need appropriate environment in order to address all of these challenges, and AWS provides such environment. Even if you are not considering public cloud for your solution, you can choose public cloud for prototyping. For instance, how are we going to start project if you don't know what hardware you need, right? Especially if you need to purchase infrastructure for big data project. I would avoid these risky investments. So I can conclude that strategy, experience, and environment is everything you need to successfully implement big data projects. And I think that's it, and we can switch to question session.
Thank you, Taras, and thank you, Serge, Vadim, and Ari, for the presentation that you've made. That was absolutely amazing. So let's move on to questions and answer session. So don't forget to submit your questions to webinar@softserveinc.com or here to our live chat. So looking through the questions, I think this one is for Ari from YOTTAA. So why didn't you use log split for your solution?
We actually did consider using log split for the solution initially, but it was decided that, based upon the number of different sources that we would get for input and the number of ways that our customers wanted us to end up using the data, we really needed a solution that was not going to be making do with hacks and extensions on top of an existing solution, but rather a custom-built solution that would integrate completely with our platform. And since we make heavy use of Amazon, and there's elements of the Lambda stack that are very complementary to our existing software architecture, it was the best process to sort of go through to work with you guys and use the custom solution that was built.
Okay, great. So here is another question, I think more technical one. What is the difference between AWS Lambda and Lambda architecture?
I think that I can answer this question. So Lambda architecture is distinct and should not be confused with AWS Lambda, which actually is a computer service. So our answer is very simple. This is two different levels. The first one is a service. The first one is software pattern or architectural pattern.
Okay, great. So here's another question: Why you didn't use AWS Elasticsearch service?
Well, let me also answer this question. So basically, it's because Elasticsearch service was introduced after we implemented the first version of our product. So I think it was October, and at that time we have the initial version of the product.
Great, thank you. I think that's sufficient. That's a sufficient answer to the question. And I think let's move on. And the last question for today. So this is definitely going to the software representatives. So guys, you've mentioned about quality attribute. What does this mean?
So quality attribute actually is a non-functional requirement. So actually it's a synonym. Examples are performance, scalability, reliability, and you may hear also about architecture drivers. So quality attribute is one of the architecture drivers among with primary use cases and limitations.
Great. So thank you all of you who joined us today. Thank you very much, our dear presenters. I think it was a wonderful presentation, and we look forward to seeing all of you in our next webinars.